What if everything you see around you, the people, the buildings, the stars in the night sky, is just a tiny fraction of what's actually out there? What if our universe is nothing more than a single page in an infinite cosmic book, with entire worlds and dimensions hidden just beyond our grasp? This isn't science fiction. It's one of the most profound questions at the heart of modern physics, and it's where the wild, mind-bending ideas of string theory come into play. Picture this: a two-dimensional creature living on a flat piece of paper, completely unaware of the vast, towering world above it. To that creature, the concept of height would be impossible to comprehend until someone lifts it into the third dimension, revealing a reality it never could have imagined. Now, what if we're the ones trapped in a limited view of existence, blind to dimensions that could be curled up all around us, invisible yet unbelievably close? String theory suggests there might be not just the three dimensions we know: length, width, and height, but as many as 10 or even 11, all woven into the fabric of space itself. These extra dimensions could be so tiny, folded in on themselves like the crinkles in a piece of paper, that we'd never notice them in our everyday lives. But if we could somehow peer into these hidden layers of reality, what would we find? Parallel universes, alternate versions of ourselves, forces and particles that defy everything we think we know about physics. The implications are staggering, and they force us to question the very nature of reality. This journey into the unknown isn't just for physicists in lab coats, it's for anyone who's ever looked up at the stars and wondered what else might be out there. Today, we're diving deep into the mysteries of string theory and the tantalizing possibility of hidden dimensions. We'll explore how scientists are using mathematics as a flashlight to illuminate these unseen realms, and what their discoveries could mean for the future of humanity. From the tiniest vibrations of subatomic strings to the mind-blowing idea that our universe might be one of many in a vast multiverse, we're about to uncover secrets that could rewrite everything we thought we knew. So buckle up, because reality is about to get a lot stranger than you ever imagined. We're all familiar with the three dimensions that shape our everyday world: length, width, and height. These are the invisible axes that let us navigate space, whether we're stacking boxes in a closet or reaching for a book on the top shelf. But there's a fourth dimension we interact with constantly, even if we don't always think about it: time. Unlike the static dimensions of space, time flows forward, carrying us from one moment to the next. Together, these four dimensions form the fabric of our reality, the stage on which everything from the smallest atom to the largest galaxy plays out. Now, here's where things get really interesting. What if those four dimensions are just the beginning? Imagine holding a newspaper. From a distance, it looks like a flat, two-dimensional sheet. But if you zoom in, you'd see the fibers of the paper curling and folding in on themselves, revealing tiny pockets of depth hidden within. That's the idea behind higher dimensions in string theory. They might be all around us, but curled up so tightly, like a straw seen from far away, that we'd never notice them without the right tools. Think of it like a hologram. On the surface, it appears to be a flat image, but when light hits it just right, a whole new layer of depth emerges. If our universe has extra dimensions, they could be doing something similar, existing right under our noses, but only detectable through the lens of advanced mathematics or high-energy physics experiments. Some theories suggest these hidden dimensions could be the key to unifying gravity with the other fundamental forces, solving mysteries that have puzzled scientists for decades. So why don't we see these extra dimensions? It's like an ant walking along a tightrope. To the ant, the rope is a one-dimensional line, a simple path forward. But to us, the rope has thickness, texture, and curves, details the ant would never experience. If dimensions beyond the fourth are compacted into spaces smaller than an atom, they'd be just as invisible to us as the rope's true shape is to the ant. Yet, if they exist, they could hold answers to questions we haven't even thought to ask. the idea of higher dimensions isn't just mathematical speculation, it's a doorway to reimagining reality itself. Whether they are curled up like coiled springs or stretched into vast, unseen realms, these hidden layers could redefine everything from the nature of matter to the origins of the universe. And that's just the beginning. At the heart of string theory lies a radical reimagining of reality, one where the tiniest building blocks of the universe aren't point-like particles but minuscule, vibrating strings. Picture a guitar string, pluck it one way and you get a specific musical note, pluck it differently and the pitch changes. Now, shrink that string down to an unimaginably small scale, billions of times smaller than an atom, and you've got the basic idea. In this framework, every particle we know, from electrons to quarks, isn't a dot but a tiny loop or strand of energy vibrating at a unique frequency. The way these strings oscillate determines whether they manifest as matter, light, or even the forces that hold the cosmos together. This elegant concept solves a puzzle that has haunted physicists for nearly a century: the glaring disconnect between quantum mechanics, which governs the subatomic world, and general relativity, which describes the vast dance of stars and galaxies. Quantum physics excels at explaining the chaos of particle interactions, while Einstein's theory beautifully models gravity and cosmic scale phenomena. But when you try to combine them, the math collapses into nonsensical infinities. String theory smooths out these cracks by replacing unpredictable point particles with the harmonious behavior of strings. Their vibrations naturally account for all known forces and particles, offering a single mathematical language that could describe everything from the birth of a black hole to the spin of an electron. But strings can't do their cosmic symphony in just 3 dimensions. The equations only balance if we introduce extra spatial dimensions, 6 or 7 more, curled up so tightly they're imperceptible to us. Think of a garden hose. From afar, it looks like a one-dimensional line, but up close you see its circular surface. Similarly, these hidden dimensions might be woven into the fabric of space itself, influencing gravity's weakness compared to other forces, or even hosting parallel universes just a quantum whisper away. While still unproven experimentally, string theory's ambition is staggering. It's not just a theory of particles, but a potential theory of everything, bridging the quantum and cosmic realms into one coherent framework. And that's why physicists keep chasing it, despite its complexities. Whether these vibrating strings are the ultimate truth or just a stepping stone to deeper revelations, they've already reshaped how we ponder existence at its most fundamental level. In the late 1960s, physicist Gabriel Veneziano stumbled upon something strange while studying the strong nuclear force, the powerful glue that holds atomic nuclei together. He found a centuries-old mathematical formula, the Euler beta function, unexpectedly describing how particles interacted at unimaginably small scales. It was like using a medieval map to navigate a futuristic city, ancient math revealing hidden patterns in the quantum world. Yet no one could explain why it worked until Leonard Susskind, Holger Nielsen, and Yoichiro Nambu made a radical leap. What if particles weren't dots but tiny, vibrating strings? This wasn't just a tweak to existing physics, it was a revolution. The strings in their equations didn't merely replace particles, they danced. Each vibration pattern corresponded to a different particle, like musical notes emerging from a single guitar string. The electron, one vibrational mode; the quark, another. Even gravity's messenger particle, the graviton, fit into this symphony naturally, something no other quantum theory had achieved. Initially, string theory faced skepticism. Many dismissed it as a clever trick for nuclear physics, not a framework for the entire universe. But in 1974, John Schwarz and Giles Shirk made a breathtaking pivot. They realized these strings could describe all forces, not just the strong nuclear interaction. If one particular vibration matched the graviton, suddenly, a theory born to explain atomic nuclei became a candidate for the holy grail of physics, a unified theory of everything. The math, however, demanded a price. Strings refused to behave in just 3 dimensions. To avoid contradictions, physicists had to introduce extra spatial dimensions, initially 5, then 9, and eventually 11 in M-theory. Imagine trying to tune a radio with static choke channels until, by accident, you twist the dial just right and catch perfect clarity. Those extra dimensions were the twist, revealing hidden harmonies in the equations. What began as an obscure tool for particle collisions now promised to weave spacetime, quantum mechanics, and cosmology into a single tapestry. It wasn't just about explaining what exists but why particles have their specific masses, why gravity is oddly weak, even why the universe has its precise structure. String theory's journey from nuclear physics to cosmic ambition reminds us that sometimes the deepest truths emerge when we follow the math into the unknown. The math behind string theory doesn't just suggest extra dimensions, it demands them. When physicists first worked out the equations, they hit a wall. The numbers only made sense if the universe had more than the familiar 3 dimensions of space and 1 of time. At first, the math pointed to 10 dimensions, 9 of space and 1 of time. Later versions, like M-theory, expanded that to 11. But why would nature need all these extra dimensions if we can't see them? The answer lies in a concept called compactification, the idea that these dimensions aren't missing. They're just incredibly tiny, curled up so tightly they're effectively hidden from view. Picture a drinking straw. From a distance, it looks like a simple one-dimensional line. But if you zoom in close enough, you'd see its circular surface, a second dimension, wrapped so small it's nearly invisible at everyday scales. Now imagine that, but with 6 or 7 more dimensions, each folded into intricate shapes at scales a billion times smaller than an atom. These hidden geometries aren't random, they're mathematically precise, influencing how strings vibrate and interact. The specific way these dimensions curl could determine everything from the mass of electrons to the strength of gravity. This isn't just theoretical hand-waving. The Calabi-Yau manifold, a complex 6-dimensional shape, is one candidate for how these extra dimensions might be structured. Think of it like the cosmic equivalent of origami, a hyperdimensional fold so intricate that it dictates the fundamental laws of physics in our observable universe. If these dimensions were arranged differently, the constants of nature might change, altering the very fabric of reality. But how could something so small have such a massive impact? Consider gravity's puzzling weakness compared to other forces. While electromagnetism can effortlessly lift a paperclip against Earth's pull, gravity struggles to keep a fridge magnet in place. String theory offers a wild explanation. Gravity might not be weak. It could just be leaking into these extra dimensions, its strength diluted as it spills into unseen folds of spacetime. The challenge is testing these ideas. If compactified dimensions exist, they'd be far too small for current particle colliders to detect directly. Yet indirect clues might lurk in cosmic phenomena like gravitational waves or the behavior of black holes. Some theories even suggest that if we could probe down to the so-called Planck scale, a realm a trillion times smaller than a proton, we might glimpse the fingerprints of these hidden dimensions. Until then, string theorists keep sculpting the math, searching for shapes that match our universe's quirks. It's like tuning a radio blindfolded, hoping to catch static resolving into music. What's fascinating is that these extra dimensions aren't just mathematical baggage. They could be the scaffolding of reality itself. The way they're folded might answer why our universe looks the way it does, why particles have their specific properties, and whether other, wildly different universes could exist just beyond the veil of our perception. The deeper we dig into string theory's equations, the more it feels like decoding a cosmic cipher, one where every hidden dimension is another twist in the puzzle. Now, let's push the boundaries of imagination even further. What if our universe isn't just in higher dimensions, but is itself a 3-dimensional island floating in a vast, unseen ocean of space? This is the mind-bending premise of the Brane world scenario. Picture a loaf of sliced bread. Each slice exists on its own, separate yet part of the whole. In this analogy, our entire universe, every galaxy, every atom, everything we know, could be just one slice, a three-dimensional membrane or brane, adrift in a higher dimensional expanse we can't perceive. This idea turns traditional cosmology on its head. Instead of extra dimensions being tiny and curled up, they could be enormous, stretching infinitely, with our Brane universe simply trapped within them. Gravity might be the only force able to leak out of our brain, explaining why it feels so weak compared to other fundamental forces. Imagine living on the surface of a pond, completely unaware of the depths below. To you, the pond's surface is your entire reality, but beneath, in the water, entirely different interactions could be happening. Similarly, other branes might exist parallel to ours, separated by dimensions imperceptible to us, each hosting its own universe with different physical laws. The implications are staggering. Collisions between branes could have sparked our universe's Big Bang, creating reality in a cataclysmic clash of higher dimensional membranes. Some theories even suggest that dark matter, the mysterious substance making up most of the universe's mass, might just be ordinary matter anchored to a neighboring brane, its gravity subtly tugging on ours like a shadow. The Brane world idea isn't just science fiction, it's a serious framework explored in variants of string theory like M-theory. If true, it rewrites our origin story. Instead of a singular explosion in empty space, our universe could be one ripple in a cosmic ocean we're only beginning to fathom. And that raises an exhilarating question. If we're just one brane among many, what or who else might be floating out there? Imagine waking up one morning and discovering your reflection in the mirror doesn't just mimic your movements, it has its own thoughts, its own life, its own version of reality. That's the eerie possibility lurking within the Brane world scenario. If our universe is just one membrane floating in a higher dimensional space, there could be countless others stacked alongside it like pages in a cosmic book, each with its own unique laws of physics, its own history, even its own versions of stars, planets, and life. Take gravity's puzzling weakness as a clue. In our universe, it's the feeblest of the fundamental forces, unable to compete with electromagnetism or the nuclear forces. But what if gravity isn't weak at all? What if it's actually as strong as the other forces, but most of its influence is bleeding into extra dimensions, leaving only a faint trace detectable in our brain? This would mean the gravity we experience is just a fraction of its full strength, like hearing a symphony through a single cracked window, missing the full richness of the music. The possibility of parallel branes opens doors to even wilder ideas. Picture two soap bubbles drifting toward each other in a sink. When they touch, their surfaces ripple violently before merging. Now replace those bubbles with branes. A collision between two membrane universes could unleash energy so colossal it would resemble our Big Bang, suggesting our entire cosmos might be the aftermath of a higher dimensional crash. Some theories propose that the mysterious cosmic microwave background radiation, the afterglow of our universe's birth, might even contain faint scars from such an event. But here's where it gets even stranger. If other branes exist, their physical laws might be nothing like ours. One could have stronger nuclear forces, making stars burn out in seconds. Another might lack electromagnetism entirely, leaving matter unable to form stable atoms. In some, time might flow backward, or entropy could work in reverse, turning chaos into order. There could even be branes where life thrives in forms we can't begin to comprehend, beings made of swirling plasma or patterns of pure energy, existing in dimensions beyond our perception. The most tantalizing question of all, could we ever detect these parallel worlds? If gravity truly leaks between branes, advanced instruments might one day catch its subtle echoes. Particle colliders could uncover anomalies, tiny missing energy that slips into other dimensions. astronomers might spot gravitational distortions with no visible source, hinting at massive structures just beyond our brain. And if another universe scraped against ours, the collision could send shockwaves through space-time itself, leaving patterns in the cosmos we could decode. This isn't just speculative daydreaming. The mathematics of string theory and M-theory actively support these scenarios, painting a picture of reality far grander than we ever imagined. Whether these hidden universes exist or not, the mere possibility reshapes how we see our place in the cosmos. We might be less like inhabitants of a solitary island and more like fish in one aquarium among countless others, each with its own rules, its own mysteries, its own version of everything. By the early 1990s, string theory had become a labyrinth of contradictions. Scientists had developed not one but 5 distinct versions, each mathematically valid yet incompatible with the others. It was like having 5 competing maps to buried treasure, all pointing to different locations. Then, in 1995, physicist Edward Witten dropped a bombshell. What if these seemingly rival theories were just fragments of something far grander? His proposed solution, dubbed M-theory, didn't just reconcile these disparate ideas. It expanded reality's blueprint entirely, introducing an 11th dimension and bizarre new objects called branes that would forever change how we imagine the fabric of existence. Think of those 5 string theories as different languages describing the same mysterious text. One version treated strings as open-ended threads, another as closed loops. Some required supersymmetry, a pairing between matter and force particles, while others didn't. On the surface, they appeared unrelated, like dialects from distant planets. But Witten revealed they were all translations of a deeper, more fundamental language, M-theory, where vibrating strings were just one piece of a much richer puzzle. At its core, this new framework suggested that strings weren't the only players. Higher dimensional membranes, or branes, could exist too, with P indicating their dimensionality. A 0 brane is a point, a 1 brane is a string, a 2 brane is a sheet, and so on up to 9 dimensions of space. Here's where it gets wild. M-theory's 11th dimension isn't just another curled-up space, it's the stage where these branes interact. Imagine 2 sheets of paper floating parallel in a windless room. In a 3-dimensional world, we'd see them hovering separately, but to flat creatures living on those sheets, each would seem like its own isolated universe, completely unaware of the other. Now replace those papers with membranous universes drifting through an 11-dimensional void, and you've got the essence of Brane cosmology. Collisions between them could ignite big bangs, while gravitational waves might ripple across dimensions, subtly influencing parallel realities. The implications ripple through every corner of physics. String theory's 6-dimensional Calabi-Yau shapes now nest within M-theory's expanded geometry like intricate clockwork. The extra dimension provides room for branes to stretch, twist, and even intersect, behaving like cosmic DVRs recording different versions of reality. Some models suggest our entire universe could be a 3-brane embedded in this higher dimensional space, with gravity's peculiar weakness arising because it's the only force not confined to our membrane. Why does this matter? Before M-theory, physicists struggled to explain why nature appears fine-tuned for life, why constants like the speed of light or the strength of gravity have such precise values. But if countless branes exist, each with different laws, ours might simply be one where conditions allow galaxies and us to form. It's the scientific equivalent of realizing your hometown isn't the only city on Earth, it's one of billions in a vast multiverse. Yet for all its elegance, M-theory remains tantalizingly out of reach experimentally. Its energy scales are so extreme that current particle colliders can't probe them, and its mathematical complexity dwarfs even general relativity. Some criticize it as untestable metaphysics, while others see it as the only path to unifying quantum mechanics and gravity. Regardless, its audacious vision has permanently altered physics' landscape, turning science's most speculative ideas into rigorous equations waiting to be solved. From vibrating strings to rippling membranes in an 11-dimensional sea, M-theory doesn't just ask what reality is, it challenges us to imagine what else it could be. One of the most stubborn puzzles in modern physics is why gravity refuses to play by the same rules as the other fundamental forces. Quantum mechanics perfectly describes electromagnetism and the nuclear forces, with particles like photons and gluons mediating their interactions through an elegant dance of probabilities. Yet when we try to apply the same quantum framework to gravity, the equations explode into infinities as if the universe itself is rejecting the math. This clash between Einstein's general relativity and quantum theory has left scientists scratching their heads for nearly 100 years until string theory offered a breathtakingly elegant solution. Gravity isn't the odd one out. It's been part of the quantum orchestra all along. Here's how it works. In string theory, every force and particle arises from the vibrations of tiny strings. But unlike open-ended strings that give rise to particles like electrons or quarks, gravity emerges from closed loops, strings that tie back into themselves like rubber bands. These loops vibrate in a specific way, producing a particle called the graviton, the theoretical messenger of gravity in the quantum realm. The sheer brilliance of this setup is that it doesn't force gravity into the quantum mold. It reveals that gravity was always quantum, just operating on a scale so subtle we'd never detected its underlying structure. Think of it like this: if the other forces are solo musicians, each playing their own distinct instrument, then gravity is the resonance of the entire symphony hall, an emergent harmony that only makes sense when you hear the whole ensemble. String theory doesn't just bolt gravity onto quantum mechanics as an afterthought. It weaves them together at the most fundamental level, with closed strings naturally generating gravitons in the same way plucking a violin string produces sound. This unification solves one of the most glaring headaches in physics, the problem of renormalization. In traditional quantum field theory, calculations involving gravity produce nonsensical infinite values like dividing by zero. But strings smooth out these infinities because they're not point-like particles, they're extended objects with finite size. This means gravity's quantum behavior isn't a bug, it's a feature emerging seamlessly from the geometry of vibrating loops. The implications are staggering. If gravitons exist, they'd be the missing link between the quantum world of atoms and the cosmic realm of black holes. They'd explain why gravity is so weak compared to other forces, perhaps because gravitons can leak into extra dimensions, diluting their influence in our observable universe. They might even hold clues about the earliest moments of the Big Bang, when quantum fluctuations in gravity could have seeded the vast structures of galaxies we see today. Yet for all its elegance, this idea faces a formidable challenge: detection. Gravitons would interact so weakly with matter that catching one would be like listening for a single raindrop in a hurricane. Current particle colliders lack the energy to produce them, and even future technologies might never spot one directly. But indirect evidence could lurk in cosmic phenomena. Gravitational waves from colliding black holes, for instance, might carry subtle imprints of higher dimensions or stringy effects. String theory's approach to quantum gravity isn't just a technical fix, it's a paradigm shift. By reimagining gravity as the vibration of tiny loops, it turns a century of frustration into a revelation that the universe's deepest laws might not be written in particles or waves, but in the intricate music of strings. Whether this symphony will ever be heard in experiments remains uncertain, but the melody it promises is too compelling to ignore. Hidden within the equations of string theory lies a mathematical masterpiece, the Calabi-Yau manifold. Picture a snowflake's intricate symmetry, but magnified into 6 dimensions, weaving a geometric tapestry so complex it defies ordinary visualization. These shapes aren't just abstract curiosities, They're the hypothetical hiding places of the universe's extra dimensions, curled into spaces smaller than a proton, yet dictating the very laws of physics we experience. To grasp their strangeness, imagine a garden hose viewed from a distance. It appears as a simple one-dimensional line, but up close you realize it's a cylinder with a circular dimension wrapped around its length. Calabi-Yau manifolds take this idea to cosmic extremes. Instead of a single extra dimension, they fold 6 into mesmerizing, multi-layered geometries, twisting like hyperdimensional origami. Computer visualizations slice through these shapes, revealing cross-sections that resemble intricate gemstones or fractals blooming in impossible directions. Each curve and hole in these structures influences how strings vibrate, determining the properties of particles and forces in our observable world. Why these particular shapes? The answer lies in their mathematical harmony. Calabi-Yau manifolds satisfy 2 stringent conditions. They're Rix-I-flat, meaning their curvature balances perfectly, like a stretched rubber sheet with no wrinkles, and admit something called Kehler structure, a precise blend of symmetry and smoothness. This makes them the only known spaces where strings can vibrate consistently across all dimensions without mathematical chaos. It's as if the universe demanded a geometric lock, and Calabi-Yau shapes were the only keys that fit. The consequences are profound. The specific way these manifolds fold could explain why we have exactly 3 generations of quarks, why the Higgs boson has its mass, even why our cosmos has more matter than antimatter. One Calabi-Yau configuration might produce a universe like ours, while another could spawn a reality where atoms never form. Some models suggest the holes in these shapes, like the voids in a Swiss cheese, correspond to families of particles, with each hole's topology shaping how matter behaves. Yet for all their elegance, Calabi-Yau manifolds pose a dizzying challenge. There are potentially billions of possible configurations, each representing a different vacuum state of the universe. This landscape problem means string theory might not predict a single unique reality, but a multiverse of possibilities. It's like tuning a radio with an infinite number of stations. Only a few might host life-friendly physics, and we're on one of them. The search for the right Calabi-Yau shape is akin to cosmic archaeology. By studying particle collisions or the fine structure of constants like the electron's charge, physicists hope to find fingerprints of these hidden geometries. Some even speculate that advanced civilizations could engineer Calabi-Yau compactifications, tweaking dimensions like dials to create custom physics. Until then, these 6-dimensional sculptures remain mathematics' most beautiful mystery, a silent symphony of shapes orchestrating the universe from the shadows. Imagine walking into the grandest library in existence, except instead of books, every shelf holds a self-contained universe with its own unique set of physical laws. Some volumes glitter with galaxies, others lie barren, their pages filled only with chaotic energy or sterile emptiness. This is the cosmic landscape of string theory, a dizzying array of possible universes numbering 10 to the 500th power, a figure so vast it eclipses the number of atoms in the observable cosmos. Far from offering a single, elegant description of reality, string theory presents us with a near-infinite banquet of mathematical solutions, each representing a different way the extra dimensions could be folded, each spawning a universe with its own quirks of physics. At first glance, this seems like a theoretical nightmare. How can a theory of everything claim to explain our universe if it also allows for countless others where gravity repels rather than attracts, or where time runs sideways? The problem cuts to the heart of science's deepest aspiration, predictability. Traditional physics aims to derive universal laws from first principles, like deducing the shape of a snowflake from the rules of crystallography. But if string theory permits every possible snowflake, then the fact that our universe has precisely 3 generations of quarks or a cosmological constant fine-tuned for life starts to feel less like inevitable math and more like a cosmic roll of the dice. This is where the anthropic principle steps in, a controversial but compelling idea that our universe's laws aren't inevitable, but simply the ones that allowed observers like us to exist. It's the razor-thin slice of the landscape where atoms can form, stars can ignite, and complexity can emerge. Picture a puddle marveling at how perfectly the hole it sits in fits its shape, unaware that the hole's dimensions are the only reason the puddle exists at all. In this view, our universe's seemingly miraculous fine-tuning isn't proof of design, it's selection bias. We're here because this particular corner of the landscape permits here to exist. Critics argue this smacks of surrender, swapping testable physics for metaphysical hand-waving. Yet the anthropic principle gains traction when paired with inflationary cosmology's multiverse. If spacetime is a bubbling foam of universes, each born with random physical constants, then statistically, some will inevitably hit the jackpot for life. String theory's landscape provides the machinery. Each Calabi-Yau manifold's geometry could anchor a different universe, with ours representing one fertile valley in a vast, arid mountain range. The stakes couldn't be higher. If the landscape is real, it implies nature's laws aren't so much discovered as localized, a shocking departure from Einstein's dream of a uniquely beautiful, inevitable cosmos. Some theorists resist this, hunting for hidden principles that might prune the landscape down to a single solution. Others embrace it, suggesting that advanced civilizations could even engineer their own pocket universes by stabilizing preferred geometries. What's undeniable is how radically this reshapes our existential perspective. We might inhabit not the universe, but a universe, one flickering candle in an endless cathedral of possibilities. Whether this diminishes or elevates our place in the grand scheme depends on how you view the dice roll. Are we the improbable winners of a cosmic lottery, or momentary witnesses to an infinite experiment in reality making? The landscape doesn't just challenge our physics, it redefines what it means to ask why. For all its mathematical elegance, string theory faces a daunting roadblock. How do you prove something you can't directly observe? The extra dimensions it predicts are either curled up smaller than a billionth of an atom, or stretched beyond horizons we can't access with current technology. It's like trying to study the grooves on a vinyl record with a sledgehammer. Our tools are just too blunt for the scale where these hidden geometries might reveal themselves. Particle colliders like CERN Large Hadron Collider smash protons together at nearly the speed of light, recreating energies last seen moments after the Big Bang. In theory, if extra dimensions exist, these collisions could produce microscopic black holes or exotic particles called Kaluza-Klein modes, ripples of gravity leaking into higher dimensions. These would decay almost instantly, leaving behind telltale patterns of missing energy in detectors. So far, no such signals have appeared, but not for lack of trying. The issue is energy. To probe the scales where extra dimensions might uncurl, we'd need a collider the size of a galaxy, a machine a quadrillion times more powerful than anything we've built. Some theories suggest workarounds. If certain extra dimensions are larger than expected, stretching a millimeter instead of a Planck length, their effects might show up in tabletop experiments measuring gravity at microscopic distances. Imagine two ultra-precise pendulums swinging nanometers apart. If gravity strengthens unexpectedly at that scale, it could hint at dimensions just beyond our perception. Other proposals involve hunting for cosmic signatures, anomalies in gravitational waves, or distortions in the cosmic microwave background that bear the fingerprints of higher dimensional physics. Even black holes offer clues. If they evaporate via Hawking radiation, the process might differ in higher dimensions, altering the radiation spectrum. String theory predicts that miniature black holes could form in colliders, but their lifetimes would be fleeting, around 10 to the minus 23 seconds. Capturing such an event would require detectors sensitive enough to catch a whisper in a hurricane. The frustration is real, but so is the ingenuity. Scientists are designing next-generation experiments using quantum sensors, atomic interferometry, and even astrophysical observations to chase these elusive hints. Until then, string theory remains a stunning map of possibilities waiting for the moment our technology catches up to its imagination. The dimensions might be hidden, but the hunt is very much alive. What if the reason gravity feels so feeble in our universe isn't because it's inherently weak, but because it's spread thin across dimensions far larger than we ever imagined? This is the radical proposition of the AD model, named after physicists Arkani Hamed, Dimopoulos, and D. Volley, which dares to suggest that some hidden dimensions might not be microscopic at all. Instead of curling up at the Planck scale, these dimensions could stretch across micrometers or even millimeters, creating unseen arenas where gravity's true strength disperses like light through a prism. Here's how it redefines everything. In our everyday experience, gravity obeys the inverse square law. Double your distance from an object, and its gravitational pull weakens by a factor of 4. But in a universe with large extra dimensions, gravity would follow a different rule, its strength fading faster with distance because it's leaking into these additional spatial realms. Picture a hosepipe spraying water in all directions. In 3 dimensions, the water spreads out, losing pressure quickly. But if the pipe were embedded in a higher dimensional space, the water would have more directions to escape into, thinning out even faster. Gravity in this scenario isn't weak, it's just diluted. The AD model calculates that if 2 extra dimensions were as large as 1/10 of a millimeter, gravity's apparent feebleness would suddenly make sense. At scales smaller than that, say, between 2 particles separated by a microscopic gap, gravity's true power would reassert itself, no longer diluted by the extra dimensions. This means that if we could measure gravitational forces at sub-millimeter distances, we might catch gravity behaving more strongly than expected, a smoking gun for hidden dimensions. Experiments are already hunting for these deviations. Torsion balance devices, which measure the gravitational attraction between tiny masses placed hairs width apart, could reveal anomalies suggesting extra dimensions. So far, no definitive signal has emerged, but the search continues. Even more intriguingly, if these large dimensions exist, particle colliders might produce microscopic black holes, not the planet-swallowing monsters of sci-fi, but fleeting specks that evaporate in a shower of Hawking radiation. Their detection would be revolutionary, proving that gravity's quantum effects become significant at energies far lower than once thought. Critics argue that large extra dimensions would destabilize the universe, causing stars and planets to collapse under altered gravitational laws. But proponents counter that Brane's membranes anchoring particles and forces to our 3-dimensional world could shield us from these effects, leaving only gravity free to roam. It's a cosmic sleight of hand. While electromagnetism and nuclear forces stay confined to our brain, gravity slips through the cracks, giving us the illusion that it's the runt of the fundamental forces. The implications ripple beyond physics labs. If gravity's scales are shifted, so too are our estimates of dark matter's behavior, the formation of galaxies, even the ultimate fate of the cosmos. And if future experiments confirm these ideas, we'd be staring at proof that reality isn't just stranger than we imagined. It's stranger than we could imagine, with dimensions vast and hidden brushing against our own, reshaping the very fabric of the universe while remaining just out of sight. Imagine standing on a trampoline, watching a bowling ball roll toward you. As it nears, its weight stretches the fabric beneath your feet, creating a depression that tugs you closer. That's how gravity works in our 3-dimensional world. Now picture that trampoline surface as our universe, a membrane floating in a higher dimensional space. But instead of the fabric stretching evenly, it warps dramatically near the brain, bending space-time so steeply that gravity's pull becomes overwhelmingly concentrated here. This is the startling vision of the Randall-Sundrum model, where hidden dimensions aren't just curled up or large, they are profoundly distorted, acting like a gravity trap for our brain. The model's brilliance lies in its geometry. In 1999, physicists Lisa Randall and Raman Sundram proposed that our universe could be perched on a four-dimensional brane at the edge of a five-dimensional bulk, a warped continuum where space-time curves exponentially like a sheer cliff face. Gravity would behave differently depending on where you stood in this bulk. Near our brane, its pull would feel normal, but venture even a microscopic distance away, and it would weaken so drastically that particles beyond our membrane would barely interact with us. It's the cosmic equivalent of living at the bottom of a deep, narrow well. From our perspective, gravity seems strong, but just beyond the rim, its influence plummets. Why does this matter? Because it solves one of physics' thorniest puzzles: why gravity is so weak compared to other forces. In this warped geometry, gravity isn't inherently feeble, it's just localized. While electromagnetism and nuclear forces are confined to our brain like paint on a canvas, gravity spills into the bulk, diluting its strength like ink dispersing in water. The steep curvature of space-time near our brain acts as a filter, letting only a fraction of gravity's full power reach us. This explains why lifting a paperclip with a magnet is effortless, while moving entire planets requires cosmic-scale effort. The Randall-Sundram model also offers a daring twist on extra dimensions. Unlike flat, evenly spaced dimensions, this warped bulk could be infinite in extent. Yet gravity would still appear weak in our universe because it's funneled into a region of intense curvature. Picture shouting into a megaphone. Your voice isn't quieter, but its energy spreads unevenly, with most of the sound concentrated in one direction. Similarly, gravity's true might be focused elsewhere in the bulk, leaving us in a gravitational shadow. What's astonishing is how testable these ideas might be. If gravity leaks into the bulk, high-energy particle collisions could produce Kaluza-Klein gravitons, exotic particles carrying hints of higher dimensional geometry. These would appear in detectors as sudden bursts of missing energy, like disappearing sparks from a firework. Some versions of the model even predict that miniature black holes could form at collider energies, evaporating instantly into telltale radiation patterns. But perhaps the most profound implication is cosmological. If our brane is anchored to a steep gravitational slope, it could explain the universe's accelerating expansion without invoking dark energy. The warped geometry itself might drive cosmic acceleration. Collisions between branes in this bulk could trigger big bangs, suggesting our universe's birth wasn't an isolated event but part of an endless cycle of creation in a warped, higher-dimensional landscape. The Randall-Sundram model doesn't just tweak our understanding of dimensions, it flips it. Space isn't a static grid, it's a dynamic, twisting fabric where gravity's rules are written not in force but in geometry. And if this vision holds, we're not just inhabitants of a universe, we're prisoners of its curvature, sensing only the echoes of a deeper, darker dimensional sea. If hidden dimensions truly exist, how would we ever know? Unlike atoms or distant galaxies, these unseen realms don't announce themselves directly, but they might leave subtle fingerprints in the fabric of reality, clues buried in the behavior of gravity or the debris of particle collisions. One of the most dramatic signatures would be microscopic black holes, not the massive monsters lurking in galactic centers, but vanishingly small ones that blink in and out of existence in a fraction of a nanosecond. According to string theory, if extra dimensions are large enough, the energy required to create these tiny black holes could drop dramatically, putting them within reach of particle colliders like the Large Hadron Collider. When two protons collide at nearly the speed of light, their energy might concentrate into a point so dense it warps space-time into a microscopic singularity. These black holes wouldn't last, they'd evaporate almost instantly via Hawking radiation, leaving behind a spray of high-energy particles as their calling card. Detecting this telltale burst would be like catching the last, fading echo of a higher dimensional whisper. Another potential giveaway comes from gravitons, the hypothetical particles that carry gravitational force in quantum theory. In a universe with extra dimensions, gravitons could have Kaluza-Klein modes, vibrational states that correspond to their momentum in the hidden directions. Picture a guitar string vibrating in multiple harmonics at once. Each note represents a different mode. These exotic gravitons would carry extra energy, but they'd quickly escape into the higher dimensional bulk, vanishing from our detectors like smoke through a sieve. In particle collisions, this would show up as events where energy mysteriously disappears, an imbalance in the cosmic ledger with no obvious culprit. While no such events have been confirmed yet, they remain one of the most tantalizing targets for future colliders. Then there's gravity itself, the force that might betray hidden dimensions through its subtle misbehavior. Newton's law of gravitation, which states that the pull between two objects weakens with the square of the distance, has been tested meticulously over centuries. But if extra dimensions exist, gravity could deviate from this law at extremely short ranges, scales smaller than a millimeter. Experiments using exquisitely sensitive torsion balances or cantilevers have searched for this anomaly, measuring the gravitational tug between tiny masses separated by gaps narrower than a human hair. A sudden strengthening of gravity at these microscopic distances would be like feeling an unexpected tug on a fishing line, hinting at unseen currents just beneath the surface of reality. These are the breadcrumbs that could lead us to hidden dimensions, fleeting black holes, vanishing energy, or gravity's secret rebellion at ultrascopic scales. Each signature is a thread in a grander tapestry waiting to be pulled, and if we ever catch one, the implications would ripple far beyond physics labs, rewriting our understanding of the cosmos, from the quantum foam underfoot to the farthest reaches of space and time. The hunt isn't just about finding new particles or forces, it's about uncovering the hidden architecture of existence itself. Among the most tantalizing remnants of the universe's fiery birth could be cosmic strings, filaments of pure energy thinner than a proton but stretching across billions of light years, forged in the first unimaginable moments after the Big Bang. These aren't the same as the tiny vibrating strings in string theory, but they share a cosmic kinship. Both are fundamental threads woven into the fabric of reality. Picture the universe cooling from a seething plasma, like a lake freezing over on a winter's night. As the temperature drops, cracks can form in the ice, except in the cosmos. These cracks would be one-dimensional defects, scars in space-time itself, vibrating with the energy of 1,000 suns. What makes cosmic strings so extraordinary is how they'd warp the space around them. Imagine looking at a streetlight through a wine glass. The light bends and distorts as it passes through the curved glass. A cosmic string would do something similar to starlight, but with a twist. Literally, it wouldn't just bend light, it would split it. The string's immense tension would slice space-time like a razor, creating double images of galaxies or stars positioned perfectly behind it. Astronomers call this gravitational lensing, but unlike the smooth curves produced by black holes or dark matter, a cosmic string's lensing would be razor-sharp, a telltale signature of its existence. Even more intriguing is how these strings might leave their mark on the cosmic microwave background, the afterglow of the Big Bang. As they oscillate across the cosmos, cosmic strings could send shockwaves through the primordial plasma, creating faint, jagged patterns in the CMB's temperature fluctuations like scratches on an old vinyl record. These patterns would be distinct from the subtle ripples caused by quantum fluctuations, offering a potential smoking gun. In 2008, a team analyzing data from the WMAP satellite thought they'd spotted such a signal, a peculiar line of temperature variation in the CMB. Though later attributed to noise, the possibility remains that future telescopes, like the upcoming Lightbird mission, might catch these ghostly imprints. The hunt for cosmic strings isn't just about proving string theory's broader framework. If they exist, they'd be cosmic time capsules, relics of an era when all forces were unified and the universe was 1 trillion times hotter than the core of the sun. Their discovery would open a window into physics at energies so extreme that even the most powerful particle colliders couldn't come close. And if they're out there threading the cosmos like invisible wires, they could be the closest thing we'll ever find to a fingerprint of the universe's first moments. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most perplexing shredders of information. Throw a book into one, and according to classical physics, it's gone forever, crushed into the singularity's infinite density. But here's the problem. Quantum mechanics insists that information can never truly be destroyed. It might get scrambled beyond recognition, but in principle, it should always be recoverable. This clash between quantum theory and gravity is the essence of the black hole information paradox, a puzzle Stephen Hawking spotlighted in the 1970s when he proved that black holes evaporate over time, radiating away their mass in a faint glow we now call Hawking radiation. If the radiation is purely random, carrying no trace of what fell in, then the information is lost and quantum physics breaks. String theory steps into this chaos with a revolutionary idea. Black holes don't destroy information, they encode it. Think of a hologram where a three-dimensional image is stored on a two-dimensional surface. Similarly, the holographic principle suggests that all the information swallowed by a black hole isn't trapped inside but smeared across its event horizon like cosmic ink on a spherical parchment. Every particle that falls in leaves a faint imprint on this boundary, a quantum fingerprint preserved in the fabric of space-time itself. When Hawking radiation escapes, it carries these imprints with it, not as recognizable data, but as subtle correlations between particles, like a jigsaw puzzle scattered across the universe. This isn't just speculation. The AD/CFT correspondence, a cornerstone of string theory, mathematically proves that a black hole's interior, a warped, gravity-dominated realm, can be perfectly described by a quantum field theory operating on its boundary. It's like realizing that the chaotic storm inside a hurricane can be understood by studying the patterns on its outer edges. In this framework, information isn't lost, it's translated, rewritten in a language that gravity and quantum mechanics both understand. Critics argue this solves the paradox only by pushing the mystery elsewhere. How does the encoding actually work? Some theories propose black holes are tangled webs of strings and branes, their vibrations storing data like a celestial hard drive. Others suggest the event horizon acts as a quantum computer, performing calculations so complex they transform matter into information. The stakes are cosmic. If string theory's holographic solution holds, it means reality might fundamentally be a lower dimensional projection, a shadow play on the walls of some deeper, stranger space. Black holes, then, aren't just graves for stars, they're burning questions pressed into the skin of the universe, challenging us to read between the dimensions. Imagine stepping into an art gallery and encountering a captivating hologram, a three-dimensional image that shimmers in midair, yet when you reach out, your hand passes right through it. The magic lies in the fact that this seemingly solid object isn't truly three-dimensional at all. It's a flat, two-dimensional surface etched with microscopic patterns, projecting the illusion of depth when light hits it just right. Now take that concept and scale it up to cosmic proportions. What if our entire universe, every star, planet, and person, isn't truly three-dimensional either, but a breathtaking projection from a two-dimensional surface at the edge of reality? This isn't science fiction, it's the holographic principle, one of the most mind-bending ideas to emerge from the collision of black hole physics and string theory. The seeds of this idea were planted when physicists began wrestling with black holes. These cosmic anomalies don't just swallow matter, they seemingly erase information, violating a fundamental tenet of quantum mechanics, that information can never be destroyed. But in the 1990s, researchers made a startling discovery. When an object falls into a black hole, its information isn't lost. Instead, it gets smeared across the black hole's event horizon, the point of no return, like invisible ink on a spherical parchment. Every particle's properties, from its spin to its charge, becomes encoded in tiny, Planck-scale fluctuations on this two-dimensional boundary. Even more astonishingly, the amount of information a black hole can store isn't proportional to its volume, as you'd expect in a 3D world, but to its surface area. It's as if the universe is telling us that the real storage space isn't inside the black hole, it's painted on its outer shell. This revelation led to a wild extrapolation. If black holes can encode 3D information on 2D surfaces, could the entire universe be doing the same? The holographic principle boldly suggests that everything we experience, the taste of an apple, the heat of the sun, the spiral of a galaxy, might just be data flickering on some distant two-dimensional boundary we can't perceive. Think of it like watching a movie on an IMAX screen. The images appear to have depth and motion, but they're ultimately just patterns of light projected from a flat film reel. In this cosmic analogy, the film reel is a vast, unseen surface at the edge of space-time, and we're the characters in the projection, utterly convinced of our three-dimensional solidity. String theory gives this idea mathematical teeth. The AD-S/CFT correspondence, a duality discovered by Juan Maldaisner in 1997, proves that a higher dimensional universe with gravity like ours can be perfectly described by a lower dimensional quantum field theory without gravity. It's like discovering that a symphony's entire score can be rewritten as a single, intricate equation, a translation so precise that no nuance is lost. In this framework, our 3D cosmos could be a holographic projection of quantum information dancing on a distant 2D surface, with every event here corresponding to a calculation happening over there in a realm we'll never see. The implications are staggering. If the holographic principle is correct, it means reality as we know it is a kind of illusion, a shadow play cast by deeper, more fundamental processes. Time and space might not be fundamental at all, just emergent properties of this cosmic encoding. Even our notions of cause and effect could be appended, with the 2D boundary acting like a quantum computer running the simulation we call existence. Critics argue this sounds suspiciously like philosophy, but the principle makes testable predictions. For instance, if space-time is pixelated at the Planck scale, a consequence of holography, our most precise experiments should eventually hit a resolution limit, like zooming in on a digital photo until you see the pixels. Future gravitational wave detectors or quantum gravity experiments might catch this grainy structure, offering empirical support for the idea. Whether the holographic principle holds or not, it's already reshaped how we think about reality's deepest layers. It suggests that the universe might not be built from particles or strings, but from information, a cosmic code written in 2 dimensions playing out in 3. And if that's true, then every thought you have, every sensation you feel, might just be a fleeting pattern on the grandest hologram of all. In the history of physics, few breakthroughs have reshaped our understanding as dramatically as the AD-S/CFT correspondence, a discovery so profound it's been called the Rosetta Stone of theoretical physics. At its core, this principle proposes an astonishing duality. A higher dimensional universe governed by string theory and gravity can be perfectly mirrored by a lower dimensional quantum field theory without gravity at all. Picture a hologram once again, but this time, imagine the entire cosmos as a projection. Every galaxy, every particle, every law of physics we experience in 3 dimensions might just be the shadow of intricate quantum interactions playing out on a distant 2-dimensional surface. The magic lies in the mathematics. In 1997, physicist Juan Maldaisner unveiled this radical connection by studying 2 seemingly unrelated realms: a hypothetical universe known as anti-de Sitter space, a warped, higher-dimensional landscape where gravity reigns, and a special type of quantum field theory called conformal field theory, which lives on the boundary of that space. The equations revealed something breathtaking. every event in the higher dimensional world, from colliding black holes to vibrating strings, had an exact counterpart in the lower dimensional quantum system. It's as if someone handed you a dictionary where every word in English automatically translates to a precise phrase in Mandarin, with no meaning lost in the process. This isn't just a mathematical curiosity. The AD/S/CFT correspondence suggests that gravity, the force that shapes planets and bends starlight, might not be fundamental at all, but an emergent phenomenon like temperature arising from the motion of countless atoms. Imagine watching a movie where the characters seem to move freely in 3 dimensions, unaware that their entire world is encoded on a flat reel of film. Similarly, our experience of gravity and dimensionality could be a cosmic illusion, with the true code of reality written in a simpler, gravity-less quantum language we're only beginning to decipher. The implications ripple across every unsolved puzzle in physics. Black holes, for instance, become far less mysterious under this framework. The information they consume isn't lost in a singularity but preserved on their event horizons, just as AD/S/CFT predicts. Even the fabric of spacetime itself might be woven from entangled quantum bits on that lower dimensional boundary, like a tapestry emerging from countless threaded connections. Yet the most thrilling possibility is practical. This duality could finally bridge quantum mechanics and general relativity. By translating insurmountable gravity problems into manageable quantum calculations, physicists might crack open questions about the Big Bang, dark energy, or even the nature of time. It's as if we've been handed a backstage pass to the universe's deepest workings, a chance to see the gears behind the cosmic clock. Of course, skeptics argue that AD/S/CFT describes a highly idealized universe, not necessarily our own. But its mathematical elegance is undeniable, and variations of the principle are already being explored in condensed matter physics, quantum computing, and even fluid dynamics. Whether it's the final word or just a stepping stone, one thing is certain. The holographic universe it reveals is stranger, richer, and more interconnected than we ever dreamed. Dark matter is one of the universe's greatest enigmas, an invisible substance that outweighs ordinary matter 5 to 1, bending galaxies with its gravitational grip, yet refusing to interact with light or any force we can directly detect. But what if its ghostly nature isn't just a property of the particles themselves, but a clue that we've been searching in the wrong dimension? Enter one of the most audacious ideas in modern cosmology. Dark matter might not be floating aimlessly in our universe at all. It could be anchored to a parallel brane hovering just a whisper away in higher dimensional space, separated from us by a gap smaller than an atom, yet utterly impenetrable to everything but gravity. Think of it like living in an apartment with paper-thin walls. You can't see or touch your neighbor, but if they play loud music, you'll feel the bass vibrating through the floor. In this analogy, the bass is gravity, the only force that can traverse the dimensional divide. Dark matter particles, then, could be dancing just beyond our brane, their mass warping spacetime enough to tug on our galaxies, while remaining forever invisible to telescopes and particle detectors. This would explain why dark matter seems to cluster around galaxies in vast, diffuse halos. It's not mixed with our matter, but draped around it like a higher dimensional shadow, its gravity seeping through the cosmic walls. The math behind this idea is startlingly elegant. In Brane world scenarios like the Randall-Sundrum model, gravity's unusual weakness could arise because it's diluted as it leaks across dimensions. But dark matter's gravitational pull wouldn't need to leak far. If its home brane is even slightly offset from ours, its influence would appear faint and smeared, matching the mysterious missing mass we observe in galaxy rotations and cosmic web simulations. Some theories even suggest that dark matter's brane could be warped or tilted relative to ours, creating variations in how its gravity bleeds through and explaining why dark matter distributions aren't perfectly uniform. But here's where it gets truly wild. If dark matter inhabits a neighboring brane, collisions between our branes could have sculpted the universe's large-scale structure. Picture two sheets of paper floating close together in a breeze. As they ripple and graze, their gravitational interactions might create patterns, like the vast filaments of galaxies we see today. These encounters could also explain odd cosmic anomalies, like galaxies with unusually diffused dark matter or voids where its presence seems to vanish entirely. The most tantalizing possibility: if dark matter's brane occasionally brushes against ours, the resulting gravitational waves could leave detectable imprints. Future observatories, like the space-based LISA mission, might catch these tremors ripples not from black hole collisions in our universe, but from far more exotic events in a dimension next door. Until then, the Brane dark matter hypothesis remains a dazzling what-if, challenging us to rethink not just what dark matter is, but where or how many layers away it might be hiding. We take for granted that time flows in one direction forward like an unbreakable arrow. But what if time isn't the singular dimension we think it is? What if, just as space has hidden folds and extra directions we can't perceive, time itself could have additional dimensions? This isn't just sci-fi speculation. It's a serious hypothesis explored in some corners of string theory and M-theory, where physicists toy with equations that describe not just one but multiple temporal dimensions. Imagine a universe where time doesn't just march forward in a straight line but branches, twists, or even loops back on itself in ways that defy our everyday experience. The idea of extra time dimensions scrambles everything we think we know about cause and effect. In our world, causes always precede effects. You drop a glass, then it shatters. But in a universe with two time dimensions, events might not have such a clean, linear sequence. An effect could ripple backward through one dimension of time while moving forward in another, like a surfer riding two waves at once. This doesn't just complicate physics, it threatens to unravel the very fabric of logic. How could you prove anything happened first if time itself is branching? Some theories suggest these extratemporal dimensions would be compactified, like spatial ones, too small to notice at human scales. Others propose they're large but constrained by bizarre symmetries that prevent paradoxes, like a cosmic failsafe keeping reality from collapsing into chaos. Time travel takes on a whole new meaning in this framework. In a single time dimension universe, traveling backward would raise all the classic paradoxes. What if you prevented your own birth? But with multiple time dimensions, you might sidestep these problems entirely. Picture a sheet of paper with two time axes instead of one. Moving backward along one dimension could simply mean veering sideways along the other, like taking a detour instead of reversing your path. Your past self might exist in a parallel thread of time, untouched by your actions. Some models even suggest that closed time, like curves, loops that return to their starting point, could exist without breaking causality as long as they're woven through extratemporal dimensions. Yet the challenges are staggering. Adding a second time dimension destabilizes the mathematics of string theory, often leading to equations that predict nonsense like negative probabilities or particles moving faster than light. To tame these problems, physicists impose constraints like requiring that extra time dimensions be tiny, or that particles are confined to specific slices of spacetime where causality still holds. It's like trying to build a house on quicksand. You need scaffolding to keep the structure from collapsing. The wildest implication: if extra time dimensions exist, they might explain why the universe seems so finely tuned for life. Just as multiple spatial dimensions could host a landscape of possible universes, multiple time dimensions might allow for alternate histories, not just branching timelines, but entire layers of causality stacked like pages in a book. Our experience of time's flow could be an illusion, a shadow cast by deeper, more complex dynamics. Whether these ideas hold up or not, they force us to confront how little we truly understand about time. We measure it, mourn its passage, and build clocks to track it, yet for all our familiarity, time remains the most mysterious dimension of all. And if string theory's boldest visions are correct, we might be missing half the story. The idea of hidden dimensions doesn't just reshape physics, it cracks open the very foundations of how we perceive reality. Over 2,000 years ago, Plato imagined prisoners chained in a cave, mistaking shadows on the wall for the full truth of the world outside. What if we're in a similar predicament, blind to dimensions that might hold the real substance of existence? Our senses and instruments are tuned to 3 spatial dimensions and the flow of time, but if there's more lurking just beyond our grasp, then everything we consider fundamental, from the solidity of objects to the nature of consciousness, could be mere projections of a deeper, richer reality. Think of an ant crawling along a telephone wire. To the ant, the wire is its entire universe, a one-dimensional path forward and backward. It has no concept of the vast world around it, the wind, the trees, the cities humming below. Now zoom out. What if our universe, with its galaxies and quantum particles, is just as limited? We might be like that ant, mistaking our narrow slice of reality for the whole picture, unaware of higher dimensional landscapes where forces and entities we can't fathom operate. This raises a haunting question: how much of what we call truth is just an artifact of our perceptual constraints? Philosophers have long debated whether reality is objective or constructed by our minds. Hidden dimensions add a new twist to this age-old puzzle. If extra dimensions exist, then the laws of physics we've painstakingly mapped, gravity, electromagnetism, even the speed of light, might be local bylaws, unique to our corner of a far vaster multiverse. It's like discovering your hometown's customs aren't universal, but just one variation in a planet of infinite cultures. Suddenly, the constants of nature aren't inevitable truths but contingent features, shaped by the way our particular universe folded its hidden dimensions. This doesn't just unsettle our scientific certainties, it upends existential ones. If we're embedded in a higher dimensional reality, free will might take on new meaning. Choices that feel linear to us could branch in unseen directions, like a tree growing roots in dimensions we can't access. Even time, which feels like an irreversible river, might be a shallow current in a deeper temporal ocean. The past and future could be as reachable as turning a corner, if only we knew how to step sideways into the right dimension. Yet for all its dizzying implications, this perspective also offers a strange comfort. The mysteries that frustrate us, dark matter's ghostly pull, quantum entanglement's spooky connections, might not be flaws in our theories but clues pointing to realities we're only beginning to trace. Every unexplained phenomenon could be a shadow on Plato's cave wall, hinting at luminous truths just outside our reach. The most humbling thought: if hidden dimensions are real, we may never perceive them directly. Our brains evolved to navigate a 3D world, not a 10D cosmos. But just as Plato's prisoners could reason their way beyond the cave, we might use mathematics and imagination to pry open the door. Whether we're simulations, holograms, or ants on a wire, the pursuit itself changes us, stretching the boundaries of what it means to be human in a universe far stranger than we dreamed. From the breathtaking tesseract seen in Interstellar to Doctor Strange's reality-bending spells in the Marvel Universe, pop culture loves to play with the idea of hidden dimensions. But how much of this is grounded in real science and how much is pure Hollywood magic? Take Interstellar's portrayal of higher dimensional space, where Cooper navigates a labyrinth of bookshelves representing time as a physical dimension. While physicists might chuckle at the visual, the core idea isn't entirely off base. The film's scientific advisor, Kip Thorne, rooted those sequences in real general relativity, where gravity can warp time into tangible, navigable structures, something string theory's extra dimensions might actually permit under extreme conditions. But here's where reality diverges. Unlike Cooper, we couldn't just punch through dimensions like tissue paper. If extra dimensions exist, they'd be either vanishingly small or require energy so extreme that accessing them would make a supernova look like a firecracker. Then there's the Marvel multiverse, where every decision spawns a new timeline, and heroes hop between realities like subway trains. It's a dazzling metaphor for the many worlds interpretation of quantum mechanics, where every possible outcome branches into its own universe. But in real physics, branching timelines, if they exist, wouldn't involve scarlet-cloaked wizards. They'd emerge from quantum decoherence, a process where particles' wave functions collapse without ever crossing into another dimension. And those portals slinging characters between universes, pure fiction. Even if alternate branes floated nearby, the energy needed to tear open a doorway between them would dwarf anything in nature. Where pop culture gets it shockingly right is the scale of dimensional weirdness. Films often depict higher dimensions as impossibly complex, folding in on themselves, a nod to Calabi-Yau manifolds, whose six-dimensional twists genuinely boggle the mind. And the idea that gravity might leak between dimensions, as hinted in Thor, The Dark World, that's straight out of the Randall Sundrum model, where our universe's weak gravity stems from it spilling into a higher dimensional bulk. But the biggest myth, that we'd experience extra dimensions like a psychedelic roller coaster. In reality, if you stumbled into a fourth spatial dimension, your brain wouldn't just see it. You'd dissolve into quantum nonsense, your atoms unraveling in geometries they weren't built to handle. Hollywood's versions are thrilling, but the truth is even stranger. Hidden dimensions, if they're out there, aren't waiting for us to explore them. They're the silent architects of reality, shaping the universe from shadows we might never directly see. The hunt for hidden dimensions isn't confined to chalkboards and thought experiments. Scientists are building machines so powerful they could tear the fabric of reality wide open. Take the Future Circular Collider, a proposed particle smasher with a ring 50 miles in circumference, dwarfing the Large Hadron Collider. If approved, this beast could reach energies 20 times higher, probing scales where extra dimensions might uncurl like petals in the quantum dawn. Imagine hurling protons together with such force that spacetime itself briefly buckles, creating microscopic black holes or gravitational echoes leaking into higher dimensions. These wouldn't be the planet-devouring monsters of sci-fi. They'd vanish in a puff of Hawking radiation. But their fleeting existence would send shockwaves through physics, rewriting our understanding of gravity's quantum roots. Meanwhile, gravitational wave astronomy is entering a golden age. The upcoming LISA mission, a trio of spacecraft floating 1 million miles apart, will detect ripples in spacetime from collisions between supermassive black holes with laser precision. If extra dimensions exist, these waves might carry subtle distortions, like fingerprints left by higher dimensional geometry. Picture dropping a pebble into a pond and seeing not just concentric circles, but strange, nested patterns hinting at unseen depths below the surface. LISA could catch gravity's whispers from branes brushing against ours, or even echoes from cosmic strings vibrating across dimensions. But perhaps the most ingenious experiments are the quiet ones happening in underground labs. Devices like torsion balancers, razor-sharp instruments measuring gravitational forces between tiny weights spaced micrometers apart, are hunting for deviations from Newton's inverse square law. If gravity suddenly strengthens at these microscopic distances, it could mean we're sensing the pull of large extra dimensions just beyond our perception. Other teams are using ultra-cold atoms or quantum-entangled particles to probe spacetime's graininess, searching for telltale signs that reality pixelates at the Planck scale, a hallmark of holographic theories. And then there's the dark horse, cosmic rays. Particles from deep space occasionally slam into Earth's atmosphere with energies far beyond what colliders can produce. If one of these cosmic bullets struck a hidden dimensions wall, it might scatter in ways that leave anomalous trails in detectors like the Pierre Auger Observatory. It's a needle in a haystack search, but the payoff proof that our universe is just one layer in a dimensional stack would be worth centuries of patience. The next decade could deliver answers or deeper mysteries. Either way, the tools we're building aren't just machines, they're bridges to the inconceivable, waiting to reveal whether reality is a flatland or a fractal shimmering with unseen depth. From vibrating strings to hidden dimensions curled smaller than atoms, from holographic universes to branes floating in higher dimensional space, our journey through the frontiers of physics has revealed a cosmos far stranger and more magnificent than we ever imagined. Yet for all we've uncovered, the most exhilarating truth is how much remains unknown. Science isn't just a collection of answers. It's an endless conversation with the universe, a dialogue where every discovery peels back another layer of mystery. Think of the pioneers who first dared to suggest that matter might be made of tiny, indivisible atoms. They had no microscopes to prove it, no equations to predict quantum behavior, just curiosity and the courage to question the obvious. Today, we stand at a similar crossroads. The mathematics of string theory and the whispers of hidden dimensions might seem abstract now, but so did the idea of black holes before we captured their shadows with telescopes. The holographic principle, the Brane world hypothesis, the cosmic landscape, these aren't just wild speculations. They're the scaffolding of tomorrow's breakthroughs, waiting for the moment when technology catches up to imagination. What's next? Perhaps the James Webb Space Telescope will spot anomalies in distant galaxies that hint at higher dimensional gravity. Maybe quantum computers will simulate Calabi-Yau manifolds, revealing which geometries match our universe's constants. Or a tabletop experiment in a basement lab could stumble upon gravity behaving oddly at microscopic scales, cracking open the door to dimensions beyond our perception. The beauty of science is that the answers often come from directions we least expect. So stay curious. The universe isn't just out there. It's everywhere, in every direction we can see and countless others we can't. Whether hidden dimensions are real or not, the quest to find them has already reshaped our understanding of reality, proving that the cosmos is richer, weirder, and more interconnected than we dared to dream. And who knows, the next great discovery might not just change textbooks, it could redefine what it means to exist. Keep questioning, keep wondering, and above all, keep looking beyond the visible. Because the greatest adventures in science always begin with a simple, thrilling possibility. What if we're wrong?